Hello, welcome to 5.2. You enjoyed exponential functions so much. Today we're going to do applications with exponential functions. What could be better? We're actually going to be applying the tools we learned from the last section. So, as we go on, applications of exponential functions. Population growth is a very popular thing with exponential functions, or it uses exponential functions. The population growth of many living organisms, bacteria, wild animals, even humans, can be modeled using the following formula. P of t equals p sub 0, means p naught, means the initial p, the initial population, times a to the t. In this formula, p sub 0, called p naught, is the initial population from the time the observer is counting. T is time and a is some base, positive number. If a is bigger than 1, the population is increasing, but if a is between 0 and 1, the population is decreasing. A certain species of fish is to be introduced into a new man-made lake. And wildlife experts estimate the population will grow according to the model P of t equals 1,000 times 2 to the t over 3, where t represents the number of years from the time of introduction. So what is the doubling time for this population of fish? How long will it take for the population to reach 8,000 fish according to this model? So for the first part, P of t is 1,000 times 2 to the t divided by 3. So this 1,000 is the initial population. So we say, okay, doubling 1,000 gives us 2,000. So 2,000 is double the initial 1,000. We divide both sides by 1,000. 2 equals t, 2 to the t over 3. So the power here is 1. 1 equals t divided by 3. So 3 equals t. So in 3 years. Now for part B, it says, how long will it take to be 1,000? Okay. So 8,000, excuse me. 8,000 equals 1,000 times 2 to the t divided by 3. I'm just putting 8,000 in place of the p of t. Dividing both sides by 1,000. 8 equals 2 to the t over 3. Now 8 is 2 to the third power. So 3 equals t divided by 3. Or t equals 9. So 9 years for the population to be 8,000. Now, a related topic is radioactive decay. Let's go on to that next. Radioactive decay. Radioactive material, through the loss of electrons, neutrons, and protons, not losses, but loses its radioactive nature. Stuff's flying off. Loses the nature, and the overall radioactive content is less than in the beginning. When we use the formula for exponential growth, but have a base between 0 and 1, we will get a radioactive decay. If we have a base of a bigger than 1, then we have a negative power to give us decay. So either we have a base between 0 and 1 to give us decay, or we have a negative power to give us decay. And they use the formula A of t equals a sub 0 times little a to the t. This means the amount at time t is the initial amount times a to the t. It's just the same as the population, because that was the population at time t equals the initial population times a to the t. So we'll use an a, capital A, instead of a capital P. And in this formula, a sub 0 is the initial amount, little a is between 0 and 1, t is the total amount of time that has passed. However, in this first example we use, the radioactive element polonium-210 has a relatively short half-life of 140 days. And one way to model the amount of polonium-210 remaining after t days is with the function a of t equals a sub 0, with the initial amount. E is a positive number, 2.7, blah, blah, blah. e to the negative has a negative power. So this is a number bigger than 1, so it has a negative power. That indicates decay. Negative 0.004951 t, where a sub 0 is the mass at time t equals 0. Note that a of 140 will have the initial amount over 2, because half of it's gone. That's what the half-life means. Half of your initial amount is gone. So what percentage of the original mass of the polonium-210 remains after 1 year? So a of t equals a naught e to the negative 0.004951 t. So after 1 year, we'll go with the year being 365 days. So 1 year equals 365 days. And we use days because the half-life is in days. If the half-life was in years, then we'd use years for our t. So a of 365 is a naught e to the negative 0.004951 times 365. And that's going to give us a naught times what? 0.1641. So this entire expression here becomes 0.1641. So it's 16.41% of the initial amount. That's how much remains after a year. So if you have a ton, you have 16.41% of that ton in the year. Or 16.41 times 2,000, we're talking about pounds, tons in terms of pounds. Okay, anyway. Now I want to just point out in the calculator, when you do this in the calculator, you're going to do E, and it automatically comes up with that power, that caret. You'll do negative 0.004951 times 365, then close parentheses after the 365. Excuse me. Now let's talk about compound interest. I expect everyone's seen compound interest formulas. Okay. An investment of P dollars at an annual interest rate of R compounded n times per year has an accumulated value after T years of A of T equals P, the principal, the initial amount, times 1 plus R over N to the NT. So let's do this problem. Example 3, Medina has $3,500. She wants to invest in a simple savings account for 2.5 years, at which time she plans to close the account and use the money as a down payment on a car. She finds one local bank, that offering an annual rate of 2.75 compounded monthly, and another bank offering a rate of 2.7 compounded daily. Will go 365 times a year. Which bank should she choose? So we're doing compounding. We have the two cases. We have the monthly case and we have the daily case. So for the monthly, the amount will be, after 2.5 years, and we're going years because it's a yearly rate. It's not a monthly rate. That'd be a great monthly rate. Okay, 2.5 times our 3,500 times 1 plus our 0.0275 over 12, because there are 12 months a year, it's compounded monthly, to the power of 12 times 2.5. And this will give us $3,748.79. In the second case, it's a daily compounding. So again, after 2.5 years, it's 3,500 times 1 plus 0.027 over 365 to the power 365 times 2.5. In this case, we have $3,744.40. So you're better off with a higher rate and the fewer compounding times in this case. Okay, so I'm saying she should choose the 2.75% compounded monthly choice. Okay, going on to the next page. An investment firm claims that its clients usually double their principal in 5 years' time. What annual rate of interest would a savings account compounded monthly have to offer in order to match this claim? So again, we're doing A of t, the amount after time t, or at time t, p times 1 plus r over n to the nt power. We want it to double. So if it doubles, it's double the initial principal. 2p equals p times 1 plus r over 12, the 12 times 5 period, because it's compounded monthly over 5 years. So we can divide out those p's. Two equals 1 plus r over 12 to the 60 power. 12 times 5 is 60. So I want to get out of this, so I'm going to do the 60th root of 2 equals the 60th root of 1 plus r over 12 to the 60th power. And this has the effect of canceling the power. So we have the 60th root of 2 equals 1 plus r over 12. I'll subtract 1 from both sides. The 60th root of 2 minus 1 equals r over 12. We solve for r. Multiply both sides by 12. And 12 times the 60th root of 2 minus 1 equals r. So r would be approximately 13.94%. 0.1394 or 13.94%. That'd be a really high rate. Okay, let's go on to the next concept. Consider the compound interest formula. In fact, I'm going to erase this and move this up because there's a whole series of things we need to discuss on this. So feel free to pause. Okay, consider the compound interest formula. A equals P times 1 plus R over N to the NT. Now, what if we compounded not monthly, daily, hourly, or even by the minute, or even by the second, but what if we compound continuously? We have an infinite number of compounding periods. Every moment of every second of every minute of every hour of every day. That is, we compound infinitely. If we set, now this is the build-up to it. If we set M equals N over R, we have our general formula. Now, M is N over R. So R times M times T gives you NT. Well, R times M times T. And over here, M is N over R, so I have R over N, so 1 over M gives me R over N. So making that substitution, if I look at P times 1 plus 1 over M to the M, then to the RT. Now this 1 plus 1 over M to the M, as M becomes infinity, this becomes E. The value E we talked about a couple of problems ago, 2.7183. And it goes on forever. E is any irrational number like pi or square root of 2 or square root of 3. It'll never repeat, never terminate, it just keeps going on. Anyway, this is one of the definitions of E. If you go on to calculus, you'll see some other definitions. But this number E is very, very popular to use in biology problems, population growth, even money growth, as we saw earlier in radioactive decay. The result of this is that as the number of times we compound goes to infinity, we get the continuously compounded interest formula. So this part becomes E. We get P times that part to the RT. A of t equals PE to the RT. This is the continuously compounded interest formula. And this is an exponential function. So E is a constant here. Let's go on to example 5. Referring to Medea from example 3, she does some more researching and finds an online bank offering an annual rate of 2.75 compounded continuously. How much more money will she earn over 2.5 years if she chooses this bank rather than the local bank offering the same rate compounded monthly? So the amount's going to be this time 3,500 times E to the R, that's 0.025, times T is 2.5. No, sorry, it's 275 here. And that's going to be $3,749.09. So I would use an A equals PE to the RT, where P is 3,500, R is 0.0275, that's a decimal form of the percent, and time is 2.5 years. Now earlier we had the other amount is 3748.79, so subtracting, she comes out with a cool, clean 30 cents extra. That's the difference. I'm going to go on to the last example. Adam is working in a lab testing bacteria populations. After starting out with a population of 375 bacteria, he observes the change in population, notices that the population doubles every 27 minutes. That's a big, oh no, it's going to take over the world type of thing, right? Find the equation for the population P in terms of time T in minutes, rounding to the nearest thousandth. Find the population after 2 hours. So we'll do P of T equals P naught A to the T. So P of T equals our initial population, we'll say, is the 375, A to the T power. We know it doubles in 27 minutes, so P of 27, it's going to be doubled, this initial amount. That's 750 is doubling this amount, which is 375 A to the 27 minutes. So if I divide both sides by 375, 2 equals A to the 27th. So if I take the 27th root of 2, 27th root of A to the 27th, A equals 1.026. So part B says find the population after 2 hours. Now this is based off a minute rate. So 2 hours equals 120 minutes. So the population after 120 minutes, it's going to be our initial population, which is 375, times 1.026 to the 120 power. And that's going to be 8,160.46. Okay, with that, increasing that rapidly, how would you be able to count that? So our formula from this part was P of T equals 375 times 1.026 to the T power. Okay, that's the answer to part A. Here's the answer to part B. Okay, and that'll do it for applications of exponential functions. I really hope you guys enjoyed that. I'll talk to you guys later. Send me your questions.